Today, we are going to see the frequency response analysis. That is, so far we have seen in time domain analysis. Hereafter, we are going to see the control system design in frequency domain. Frequency domain analysis. Frequency domain analysis. How we'll get the frequency response of the system? I think you might have done some experiment in an electronics lab. You will be given with the amplifier. You will be given amplifier. For that amplifier, you will be asked to find the frequency response. What you will do is you will give me a sinusoidal input. Sinusoidal input you will give with the constant amplitude. Constant amplitude. Input will be constant amplitude. For that, you will get the output for a linear system. Amplifier is a linear system. For a linear system, the output also a sinusoidal system, signal. Sinusoidal sine signal. Input is sine wave, output also sine wave. You will, but you are keeping the amplitude constant, but you will vary the frequency from 0 to maximum possible value. For that, for every frequency, you will measure the magnitude. You will measure the magnitude and note down. Finally, you will draw the frequency response. The frequency response you will draw. It is you will take a logarithmic scale in x-axis and decibel scale in y-axis, and you will draw the frequency response for that amplitude for different input frequencies. You will get a response like this. A trapezoidal signal like this you will get. You will be asked to find the cutoff frequency. That is 1 by root 2 times of the magnitude of this magnitude. This is the ultimate or the maximum magnitude you got. From there, you will be subtracted 1 by root 2 times and you find the magnitude. At that point, what is the frequency? That is called lower cutoff frequency. Similarly, you will find 1 by root 2 times here. That is called upper cutoff frequency. Upper cutoff frequency. Between these two is called bandwidth. You will be asked to find the bandwidth of the amplifier. What is you noted here? As frequency decreases, the amplitude is decreasing. Similarly, as the frequency increases here, amplitude decreasing. In between, the amplitude is constant. That you can notice. So the system gives different response for different frequencies. That we are going to do here. Here, this is the transfer function. For that, you are giving a sinusoidal input as input. You are getting a sinusoidal signal as output. This is the input signal. This is the output signal. For the given frequency, here this is the amplitude is A, but here amplitude we got is B. This is called the magnitude response. Magnitude, frequency response, magnitude response. You can also notice that there is a phase shift here. Between input and output. You know that for an amplifier, the total phase shift is 180 degree. The total phase shift is 180 degree for all frequencies. Let us assume. So, what is if you give signal like this as input here, if it is an amplifier, you will get the phase shift like this, 180 degree phase shift. If you draw the response for this phase shift, if you measure for different frequency, what is the phase shift if you measure? And if you draw the response, then it is called phase response. But in the lab, you did only magnitude response. You did only magnitude response.
We see the difference between input and output signal. Not only there is a change in amplitude, not only there is a change in amplitude, but also there is a phase shift. The signal starts here, but the signal starts here. It means what? There is a phase shift. There is a phase shift because of it is passing through this G of S. There is a phase shift phi because of it is passing through this transfer function. If you record the phase shift also, then you can plot another response that is called phase response. That is called phase response. Phase response. That is also between log F versus phase shift. Suppose this phase shift is constant. Always there is a 90-degree phase shift. Lag phase shift means you can draw a horizontal line minus 90 degree. It means there is a constant phase shift. Constant phase shift. Always there is a delay in 90 degree. That way you can say. Suppose always there is a phase shift of plus 90 degree means that is also a horizontal line. Suppose the phase shift is changing means you will get inclined line. That is called phase response. So there are two responses, frequency responses. How we have to obtain? The input signal is sinusoidal signal. Input signal is sinusoidal, sine wave, with variable frequency, different frequency. For each frequency, we measure the magnitude, we plot, that is called magnitude response or magnitude plot. Another one is called phase plot. Another one is called phase plot. What is the phase difference between input and output? We know that for a transistor, what is the phase shift? Suppose you are giving an input signal here. What is the phase shift for a transistor? There is a delay in 90 degree. So, 180 degree phase shift. 180 degree phase shift. If you give a signal like this, there is a 180 degree phase shift like this in the output. If it is common emitter amplifier, 180 degree phase shift. So that phase shift is constant for all frequencies means you will get a horizontal line like this. That is called phase response. In electronics lab, you plotted only amplitude response. You plotted only amplitude response. You didn't consider that phase response since it is constant. But here we consider both amplitude response as well as phase response. Both we will consider. What is the output? The output C of t equal to the input amplitude is A. Input amplitude is A. A multiplied by, it is, suppose you are assuming it as an amplifier of gain G means it should be multiplied by modulus of G of j omega. You are assuming that it is a gain of G. That's why it is multiplied by G of j omega. Multiplied by the signal is input also sine omega t, output also sine omega t. There is no change in frequency, but there is if it is a linear system. If it is a linear system, there won't be any change in frequency. That is output also sine omega t. The amplitude is modified by A times G of j omega. The input signal amplitude is A, but the output signal amplitude is A times modulus of G of j omega. So amplitude is equal to B. Let us call this is equal to B. B equal to A times modulus of G of j omega multiplied by sine omega t. That's all. There is no change in frequency, but there is a phase shift. That's why that phi of omega is added to that omega t. There is a phase shift. Shift in phase. Shift in phase. That's why the output signal is B omega sine omega t plus phi of omega. Suppose if A equal to 1 means, what is B of omega? B of omega equal to modulus of G of j omega. If A equal to 1, if A equal to 1 means, if A equal to 1 means A times modulus of G of j omega is nothing but G of modulus of G of j omega because A equal to 1. What will happen to the phase angle phi of omega is because of phase shift introduced by angle of G of j omega, angle of G of j omega. Therefore, what is the change between input and output? The magnitude is changed by B of omega times. That is modulus of G of j omega times. What is the change in phase shift? Angle of G of j omega. Here you notice that the phase shift added is angle of G of j omega. That's why the magnitude response is nothing but modulus of G of j omega. The magnitude response is nothing but a modulus of G of j omega, because B of omega equal to B of omega, the output amplitude equal to modulus of G of j omega when A equal to 1. Similarly, the phase angle equal to angle of G of j omega. That's why to get the frequency response, magnitude plot as well as phase plot, we are plotting modulus of J of j omega for magnitude plot and angle of J of j omega for phase plot by varying omega from 0 to infinity. By varying omega from 0 to infinity. So the magnitude plot is modulus of G of j omega by varying omega from 0 to infinity. What is omega? What is G of S? Suppose I am having a first order system means K upon tau S plus 1. If you replace S by j omega, then it is called frequency transfer function. G of j omega equal to K upon j tau omega plus 1. J tau omega or j omega tau, like that you can write, or you can write K upon j omega tau plus 1. This is called the frequency transfer function. If you vary omega, that is frequency, from 0 to infinity, you will get magnitude plot as well as phase plot. How to draw this phase plot and magnitude plot without conducting experiment? That we can do. There are methods to find frequency response. The frequency response will be looking like this. For any G of S, if you plot, it will be like this. This frequency response will be looking like this. Here, the specification, frequency domain specifications can be found from this frequency response. Time domain specifications we found in that response. This is overshoot MP. This is overshoot MP. TP. At this time, this is called TP. Raise time TR. And settling time TS. These are all we found in time domain specifications. Like that, here also we can specify some responses. At one point, the magnitude, output magnitude, at particular frequency, the output magnitude will be very high. That magnitude is called MR. That magnitude is called MR. That frequency is called omega R. That MR is called resonant peak. Resonant peak MR. That frequency is called a resonant frequency omega R. At resonant frequency, the amplitude, output amplitude will be maximum. Here, as frequency increases, the amplitude go on decreases. Amplitude go on decreases. The response will be, approximate response will be like this. It go on decreases amplitude. At one particular point, the amplitude is reduced by 1 by root 2 times this value. Suppose this magnitude is 1 means at this point the magnitude is 1 by root 2 times. 1 by root 2 times decreased. This point is called this cutoff frequency. This cutoff point, the frequency at this point is called cutoff frequency. Cutoff frequency. Here, if you tell in decibel scale, this magnitude is 3 dB. 3 dB. The amplitude is reduced by 1 by root 2 times. And it's in decibel scale, the amplitude is reduced by 3 dB. Suppose here, the amplitude is 1 means 0 dB here. That's why at this point, minus 3 dB. This point may also be called as minus 3 dB point or cutoff point or cutoff frequency, the frequency at which it occurs. is the cutoff frequency. Here, the bandwidth, the range of frequency from 0 to at this FR is called or omega R. We can say FR or omega R. If radians means omega, hertz means F. So here, this bandwidth, this width is called bandwidth, omega R. The frequency up to which the magnitude is within the 3 dB bandwidth. That is called bandwidth. So bandwidth is omega R minus 0, that is equal to omega R. If you tell in hertz, FR minus 0 equal to FR. It is only right-sided signal, right-sided signal. There is no left side, one-sided signal. The slope at which it decreases here, the slope at which it decreases here is called cutoff rate. This point is called cutoff point. Cutoff point. At cutoff point, what is the slope? That slope is called cutoff rate. It decreases at so many dB per decade. Like that we can tell. So this is called cutoff rate. The speed at which it decreases is cutoff rate. Gain margin and phase margin I will let you later. Gain margin and phase margin we'll see later. These are all frequency domain specifications. These are all called frequency domain specifications. Let us see once again. Resonant frequency means the frequency at which the amplitude is maximum. The maximum amplitude, MR, is called resonant peak. Cutoff frequency is the frequency at which the magnitude is reduced by 1 by root 2 times, or the magnitude is reduced by 3 dB. That point is called cutoff. The frequency at which it reaches is called cutoff frequency. The distance between 0 and cutoff frequency, omega R, is called bandwidth. The bandwidth is omega R minus 0, that is equal to omega R. If we are talking in terms of hertz, then it is called FR minus 0, that is equal to FR. The slope at the cutoff point is called cutoff rate. Gain margin and phase margin are relative stability that we will see later. I will let you know later. The frequency plots, there are the 5 different frequency plots are there. One is linear frequency plot. In the linear frequency plot, the x-axis will be in linear scale and y will be also in linear scale. Then it is called linear plot, linear frequency plot. Another one is linear magnitude versus log plot. Here, this alone is taken in logarithmic scale, log f, but magnitude is in linear only. Semilog sheet, you will draw in semilog sheet, that is called linear magnitude versus log plot. The third one is called Bode plot, that we are going to learn. Bode plot means this is in logarithmic scale, x-axis in logarithmic scale, y-axis in decibel scale. Decibel scale. This g of j omega is taken 20 log modulus of g of j omega. If you take, that will be in decibel scale. So y-axis in decibel scale, x-axis in logarithmic scale means then it is called logarithmic plot or Bode plot. Both are in logarithmic scale. Y-axis as well as x-axis, both are in logarithmic scale. Then it is called Bode plot. The another plot is called Nyquist plot. Here, the x-axis is in frequency scale, y-axis is in magnitude. If you plot only magnitude, if you didn't consider, and this linear, all these plots, first is what? Linear frequency plot. Second one is linear magnitude versus log omega plot. Third one is Bode plot. In all these cases, we can draw both magnitude as well as phase. Both magnitude as well as phase. 2 plots are there. One is magnitude plot, another plot is called phase plot. This is called phase plot. Angle of g of j omega versus log f. Log f. This is called phase plot. This is called magnitude plot. magnitude. Both we can plot for 1, 2, 3. The fourth plot is Nyquist plot or polar plot. In that we are not taking F on axis. Instead, we are plotting in a polar chart. Polar chart means it will be like this. Circles will be there. Circles will be there like this. This is 0 degree, 90 degree, 180 degree, 270 degree, again 360 degree. So the angle will be given like this. See, 10 degree, 20 degree, like that it is given. 90 degree, 180 degree, like that. These axes will be there. So we can plot in polar way. We can represent in 2 coordinates. One is rectangular coordinate. Rectangular coordinate, this is this axis is real axis. This will be imaginary axis. The same can be represented in polar way. Magnitude versus angle. Morning also we have seen one sum in that this pole is at a distance of 3, omega n equal to 3, and its angle is cos inverse of 0.5, that is 60 degree. So we can say 120 degree. This point can be represented as 3 angle 120. So that way we can plot between magnitude and phase. For each frequency, we know the magnitude. For each frequency, we know the phase. If you plot magnitude and phase, you will get a plot in polar chart. This chart is called polar chart. Polar chart. In the polar chart, each point you have one magnitude, one angle. Phase angle, magnitude. Phase angle, magnitude. You can combine and you can draw the plot. That is called polar plot. Suppose you are drawing a polar plot for a first order system. Polar plot for a first order system. You will get a plot like this. You will get a plot like this. This is called polar plot. For omega equal to 0, you got here when omega equal to infinity, because we plot the frequency response from omega equal to 0 to infinity. If you vary the frequency, you will get plot like this. You will get plot like this. This is first order plot. First order system. Polar plot. Or Nyquist plot. We can call it as polar plot or Nyquist plot. If you draw for second order system, if you draw the polar plot for second order system, 1 by s multiplied by s plus tau s plus 1. For that, if you vary omega, this is g of s. What is g of j omega? G of j omega equal to 1 upon j omega multiplied by tau j omega tau plus 1. Here, if you vary omega from 0 to infinity, if you vary omega from 0 to infinity, you will get a plot. If you substitute omega equal to 0, what you will get? Infinity. 1 by infinity. Therefore, 0. 1 by 0, infinity. You will get infinity. Angle will be 90 degree. I will tell. We'll see all those things later. But anyhow, I'll tell you. Angle will be minus 90 degree. Magnitude will be infinity. So, if you draw the type 1, what is the type number? Type 1, second order polar plot means it comes from here and it will be like this. If you draw the type 1 third order system, it will be like this. So these are all we'll see later. How it came and all we'll draw. Actually, we'll draw. Nyquist plot we'll draw for different transfer functions. We'll see later. But if you consider a third order type 1 system, its Nyquist plot or polar plot will be looking like this. This is 0 degree. This is 90 degree. This is 180 degree. This is 270 degree or minus 90 degree. Angle will be initially minus 90 degree. That's why it comes from here. And finally, it comes to 0. Because when omega equal to infinity, amplitude becomes 0. That's why finally it approaches 0. Here, if it crosses at 180 exactly at -1, that is marginally stable system. If it crosses after this -1, then it is called unstable system. Then it is called unstable system. So if it crosses 180 before -1, if it crosses 180 degree before -1, we can say that the system is stable. In root locus, how we find stable system and all? If it crosses j omega axis, we are saying that it becomes unstable. It becomes unstable. Like that here also, if we increase k, suppose here the value of k is k1, here this is k2, here it is k3. The same frequency response is plotted for different values of k. This is for k1, Nyquist plot is plotted. This is for k2, Nyquist plot is plotted. For the same system. For k3, this is plotted. Here, when k equal to k max, it passing exactly through -1. When k is less than k max, it is crosses 180 before -1. Therefore, this is stable. This is marginally stable. This is unstable, we can say. So we can say that the system can be bring to stable state by decreasing k. Because if you decrease k, the plot will cross -1. The plot will cross 180 before -1. The plot will cross 180 before -1. So we can talk like that. In other words, if you increase this much k, it will cross -1. If you increase this much k, it will cross -1. That is called gain margin. I told you that I'll explain this later. So with this plot, I cannot explain that. If you increase k, the frequency response will be amplified. If you increase k, output to magnitude will increase, That's why the plot will amplify like this. But it becomes unstable. Because it crosses 180 after -1. So by using this frequency response, we can say that this much k is required to become unstable. That is called gain margin. We'll see later about gain margin. We'll see later about gain margin in detail. But now I can tell this way only. So gain margin means this much k is required to make the system unstable. That is called gain margin. Or I can say that, suppose at this point, what is the phase angle at this point? This is the phase angle for this, because this is the phase angle. Phase angle means the angle of g of j omega. This plot is plotted between magnitude of g of j omega versus angle of j of j omega. No frequency is considered to plot this plot. No frequency is considered. For particular frequency, what is the magnitude? What is the phase? That point is marked. Then for next frequency, what is the magnitude? What is the plot? Next frequency, what is the magnitude? What is the phase? For next frequency, what is the magnitude? What is the phase? Like that, for many frequencies, you will find all these points and it is plotted. You can notice that if k is increased, the plot is magnified. Therefore, in other words, how much gain is required to bring the system in the verge of instability? That is called gain margin. Suppose you are having the original plot is like this. It crosses -1. It crosses 180 before -1. Suppose you increase k so that it goes through this -1 means how much k is increased? K is increased by 3 times. K is increased 3 times. Therefore, gain margin is 3. Gain margin is 3. If I increase gain 3 times, system becomes unstable. If I want to tell this in decibel scale, 20 log 3. 20 log 3 is the gain margin in decibel scale. In linear scale, 3 is the gain margin, because suppose the present gain is 1 means when gain equal to 3, it becomes marginally stable means 3 is the gain margin. In decibel scale, 20 log 3. Initially, gain is 10. If you increase 30 gain, it becomes unstable means how much it is increased? 3 times increased. Therefore, gain margin is 3. Suppose the initial gain is 5. When it becomes 50, it becomes unstable means how much gain is increased? 10 times increased. Therefore, gain margin is 10. If we talk the 10 in logarithmic scale, decibel scale, 20 log 10 is the gain margin. So gain margin means by what factor we have to multiply the gain K so that the system becomes in the verge of instability. So the factor is 3. The first case, gain of the system is 1. If we make the gain of the system equal to 3, it becomes unstable. Therefore, factor is 3. In the second system, the gain of the system is 10. When it becomes 30, it becomes unstable. Gain of the system becomes 30, it becomes unstable. Factor is 3. If you multiply by 3, it becomes unstable. Therefore, gain margin is 3. The third system we have seen, initially its gain is 5. If it becomes 50, it becomes unstable. The factor is 10. If you multiply 10-fold, 10 times if you increase the gain, the factor is 10. Therefore, gain margin is 10. If we talk the gain margin in decibel scale, 20 log 3 first for the first system. Second system also 20 log 3. Third system also, third system is 20 log 10. 20 log 10. So that is called gain margin. What is phase margin? To understand phase margin, we'll consider the same type 1 third order system. Type 1 third order system. If you increase the gain, it amplify like this. If you increase the gain, it amplify like this. So if you increase gain, it becomes unstable. I am not increasing the gain, but I am increasing the phase shift. What happens? If I increase the phase shift, what happens? For example, this is the system. The phase shift for a frequency omega 1 equal to, say, what is this angle? Up to this 90 plus 45, 135. So we can say that 135 degree at this point. If I increase this 135, I'm adding another 180 minus 135, how much? 45. If I add another 45 degree minus 45 degree to the system, I'm introducing a phase shift. I'm introducing phase shift only. I'm not changing the gain. Only introducing phase shift. Then what will happen? This point will move along this plot and comes here. Am I correct or not? Am I correct or not? This will move, comes here. So the same point will move along like this. Suppose I'm having a unit circle. I'm having a unit circle like this. I'm having a unit circle like this. This plot crosses the unit circle here. Unit circle here. This is minus j. This is plus j. This is minus 1. This is plus 1. Am I correct? Unit circle. Here, the angle is not 135. Let it be 90 plus 20. How much? 110. 110 minus 110. I am introducing a phase shift of how much? 180 I required. I am introducing, here it cuts the unit circle. Here it cuts the unit circle. Here the angle is 110. I want to make it minus 180. How much I have to add? 70. If I add 70 degree at this point, the same frequency without changing magnitude, if I add minus 70 degree, what will happen? This point will move and come here. So if I introduce phase shift also, the system becomes unstable. It becomes marginally stable. So when it crosses minus 1, the system becomes marginally stable. But I am not increasing any gain, but I introduce only phase shift. Because of that phase shift, it becomes unstable. That's why the phase margin is 70 degree. The phase margin is 70 degree because it has 110. If I introduce phase shift only into that system, now I'm not increasing the gain. Only phase shift is introduced, the system becomes marginally stable. That's why the system has a phase margin of 70 degree. That is called phase margin. That is called phase margin. So the gain margin and phase margin also frequency domain specifications. And now Nyquist plot means polar plot. Nyquist plot means polar plot. Nichols plot means that is also polar plot plotted on a Nichols chart. If you plot the polar chart in a Nichols chart, then it is called Nichols plot. So we are going to study about these three only: polar plot, Nyquist plot, and Nichols plot. These three, if you draw the Nyquist plot on a Nichols chart, then it is called Nichols plot. These are the three plots that we are going to see.